Okay, hello everyone. In a new video, so we have reached part 2 of chapter 6, which is the chapter of center of mass for grade 11 students. In this video we are going to solve some exercises. Let's start by exercise number 1. A rod constructed for electrostatic experiments is formed of an insulating handle of glass of length 20 centimeters. So let me say here that the glass is made up of length L1 is equal to 20 centimeters and of density ρ1 is equal to 2000 kilograms per meter cube. The other part of the rod being made of brass of length 20 centimeters and of density 1000 kilogram per meter cube. So brass of length L2, say for example 20 centimeters, and ρ2 is equal to 8000 kilogram per meter cube. So recall that the SI unit of density is given by kilogram per meter cube. So this is equal to 0.2 meters in the SI and 0.2 meters in the SI. Okay, knowing that density, mass, and volume are related via the following formula. Okay, now they are telling me determine the position of the center of mass of the rod. So recall that we must admit or follow several steps in order to determine the center of mass. So step number 1 is to choose a reference system. Step number 2, coordinates of different bodies. Step number 3, write the barycenter formula. And step number 4, do the projection. Okay, so they are telling me to determine the position of the center of mass of the rod. So notice that here the rod consists of two bodies that are made up of brass and glass. So suppose that this is the object A and this is the object B. So here we need to choose first the reference system. Independent of our choice, the result will be the same. For example, first we need to choose the origin. We can choose the origin to be at this point, or at this point, or even at this point. Our result will be independent of the chosen reference system. Suppose that in this case we will take the origin to be this point. So in this case all the positions will be positive. So suppose that this is the x-axis and this is the y-axis. And here, as for the x-axis and the y-axis, they are labeled by the quantity, which is meters. Okay, so we are done with step number 1. Let's refer to step number 2, which is coordinates of different bodies, for sure the center of gravity. Now notice that the brass is made up of uniform material because the density is specified and it is given to be constant. So suppose that this is the body 2. Let me say that this is 2 and this is 1. So G2 representing brass will be here at the center of this material. So this is G2, and as for glass, this is G1. Now let's locate the coordinates of G2 and G1 with respect to the origin O. So as for G1, now if this is 20 centimeters, so the half of this is stand, so this is given by 30 centimeters, which is 0.3 meters. And as for the ordinate, it's given by 0. As for G2, the coordinates of G2 are given by 0.1 meters and of 0 ordinate. Now we are ready to use the barycenter formula. So let's write the barycenter formula, which is given by OG is equal to summation of MI OGI divided by MI summation of MI. So notice that this is a vector relation. Vectors must exist on the left and on the right. Now I represent the number of objects that we have. In this case we have glass and brass, so I will run from 1 to 2. So this formula is given by M1 OG1 plus M2 OG2 divided by the factor of M1 plus M2. So in this case we have that OG factor is equal to M1 OG1 plus M2 OG2 divided by M1 plus M2. So the next step is to project. Let's start by the x-axis. So projection along the x-axis. So always a vectorial relation can be decomposed into its x and y components simply by dropping down the vector and carrying the label and labeling vector quantities by x. So in this case we have OGX is equal to M1 OG1x plus M2 OG2x divided by M1 plus M2. So what does OG1x? It represents the abscissa of G1, which is, say, for example, given by x1. So M1 x1 plus what does OG2x represent? It's the abscissa of the point G2, which is given by x2, say, for example, M2 x2 divided by M1 plus M2. So this is x1 y1, this is x2 y2. So now in this case, notice that we don't know the values of M1 and M2, but we know the values of the densities. However, let me proceed now and say that, okay, the value of x1 is given by 0.3 and the value of x2 is given by 0.1 divided by M1 plus M2. So OGX, which represents the abscissa of the center of gravity G of the system consisting of brass and glass, is given by 0.3 M1 plus 0.1 M2 divided by M1 plus M2. Now, in order to determine the value of xg, we should determine the values of M1 and M2. So now, knowing the density, so the density and the mass are related via the following formula. So in this case, mass can be written as density multiplied by volume. So but density is equal to mass multiplied by volume. So in this case, if rho carries the index 1, then the mass will carry the index 1 and the volume will carry the index 1. So recall that density is equal to mass divided by volume. So whenever we are specifying the density of a certain object labeled by the index 1, then we are talking about its mass, which is given by M1, and its volume, which is given by M1. Okay. Now similarly, rho 2 is given by M2 multiplied by V2. So now replacing the expression of rho in xg, what do we have? We have xg is equal to 0.3. Sorry, we are interested in determining the expression of M and not rho. Sorry, this is completely wrong. So here we have that mass is equal to rho multiplied by V. Recall that if rho is equal to M divided by V, then M is simply given by rho multiplied by V. Okay. So in this case, if M carries the index 1, rho will carry the index 1 as well as V1. So then M1 is equal to rho 1 multiplied by V1 and M2 is equal to rho 2 multiplied by V2. So replacing the value of M by this expression, plus 0.1 Now notice that they are telling me that L1 is equal to L2 is equal to 20 centimeters. So what do they mean by this? They mean that the volume of the brass and the glass is the same. So the volume is related to the length and to the width of this road, and since they have specified the length is the same and they didn't mention anything about the thickness or the width of the brass and the glass, so we suppose that V1 is equal to V2. So let me here say between brackets that V1 is equal to V2 since L1 is equal to L2, because the volume is related to the length, and here we are not specifying the width and the height, because we know that for a rectangular shape the volume is equal to length times width times height. Since they didn't specify anything about the width and the height, so we consider that they are equal. So let me say that V is equal to V1 equal to V2, so this is equal to 0.3 rho 1V plus 0.1 rho 2V divided by rho 1V plus rho 2V. Now taking from the numerator V as a common factor, we have 0.31 rho 1 plus 0.1 rho 2 divided by V rho 1 plus rho 2. Now we can simplify by V. So as you can see that in this case the volume is not important, it simplifies. Now the value of rho 1 is given to be 2000 and rho 2 is given by 8000. So this is equal to 0.3 multiplied by 2000 plus 0.1 multiplied by 8000 divided by 2000 plus 8000. Let me make sure of the numbers. Okay. Now plugging this fraction on the calculator, then the value of xg is given by 0.14. Since everything is expressed in the SI, so the value of xg will be expressed in the SI, which is meters, which is equal to 14 centimeters. So why I have converted this value to the centimeters, because the dimensions is given by centimeters. Okay, so now let me say that xg is equal to 14 centimeters. Now as for the projection along the y-axis, we drop down the vector, and each vector quantity will carry the label y. So OGY is equal to M1 OG2y plus M2 OG2y, this is 1, divided by M1 plus M2. So now notice that the value of so this is equal to y1 plus M2 y2 divided by M1 plus M2. So now notice that the value of y1 is 0 and the value of y2 is 0. So this is simply equal to 0 divided by M1 plus M2. So this is 0 because anything divided by 0 is 0. Then YG is equal to 0. So in this case, the coordinates of the center of gravity of the system is given by G, which is given by 14 centimeters and 0. And the vector notation is being expressed as 0.14i plus 0j. And let's check the location of the center of gravity. So actually it must be somewhere between G1 and G2, so this number is not reasonable. Let me check the calculation again that I've done here. The answer is correct. Let me see. No, okay, the answer is correct. Now you will see why. So if this is 10 centimeter, now notice that I'm interpreting this result from a physical point of view. So 14 centimeter, so G1 is located here and G2 is located here, then we expect that the center of gravity G, because it's the average between G1 and G2, must be somewhere located between G1 and G2. Now, because brass is more dense than glass, then the center of gravity must be shifted toward G2. So we expect that the center of gravity, if this is the midpoint, so we expect that the center of gravity must be somewhere here. And indeed, if you check the result, it's given by 14 centimeter. This is 10. So 14 centimeter must be somewhere here. This is 20, this is 15. So this is the location of center of gravity G of the system, which is given by 14 centimeters, 0. For sure, we are measuring G with respect to the origin. Okay, this result is reasonable because notice that rho 2 is more dense than rho 1, much greater. So as this number increases compared to rho 1, then G will be shifted toward G2. Okay. Now, exercise number 2, they are telling me the mass of Earth is 81 times the mass of Moon. So let me say that ME is equal to 81 the mass of the Moon. So this is the Earth and this is the Moon. And the distance of the center of the Moon from the center of the Earth is 384,000 kilometers. So the distance d separating both planets, the center of gravity of both planets or the center of masses, is given by 384,000 kilometers. Knowing that kilometers is not the SI unit of distance, in order to convert from kilometers to meters, we multiply by 10 to the power 3. So this is given by 384 times 10 to the power 6 meters. Now they are telling me determine the position of the center of mass of the system. So this system is the system S, consisting of the Earth and of the Moon. And then they are telling me, is this center of mass above or below the surface of the Earth? So this is the center of the Earth and this is the surface of the Earth. So they are telling me, given the radius of the Earth is given to be 6,400 kilometers, so the distance from this point to the circumference is given by 6,400 kilometers, or the peripheral of the surface of the Earth, because Earth is considered as a sphere. So because they're asking me about the center of mass of a system consisting of more than a body, then we are interested in applying the barycenter formula, and this consists of several steps. So step number 1, coordinates of different bodies. So before, we need to choose a reference system. So recall that the steps are given by choose a coordinate of reference system, coordinates of different body, then write the barycenter formula, then project. So in this case, let me say that step number 1 is given by choose a reference system. Step number 2, coordinates of bodies or the center of masses of the body. Step number 3 is given by the barycenter formula, and step number 4 is given by the projection. So here we need to choose a convenient reference system. We can choose it in infinite number of ways. The simplest one is to consider the x-axis as the line that joins the two center of masses. So this is the x-axis. As for the y-axis, this is the y-axis, which is perpendicular to the x-axis. And recall that the y-axis and the x-axis are labeled by physical quantities that are given by meters. And this is the origin O. Okay, so the origin O is chosen to be the center of gravity of the Earth. Now this is this is G1. Let me say that this is G1 and this is G2. at the points C1 and C2. This is C1 and this is C2. Okay. So now, after we have chosen the reference system, we need to locate the coordinates. Then in this case, G1 is simply given by 0, 0, which coincides with the origin. As for G2, notice that G2 is separated from G1 by the distance, which is given by D, which is 384 times 10 to the power 6 meters. And it's positive because we are measuring it with a positive direction. As for the ordinate, it's given by 0. So here notice that because the ordinate is 0, no need to project along the y, but we will project and check that the ordinate of the center of gravity of the system is given by 0. Now the next step is to write the barycenter formula, which is given by OG is equal to summation of mi OGI divided by summation of mi. Here, what does I represent? I is the number of objects we have, which is given by 1 and 2. Then the index I will run from 1 to 2. So it's given by M1 OG1 plus M2 OG2 divided by M1 plus M2. Notice that this vector is only for OG2 and not for M2. This vector is only for OG1 and not for M1. And vectors must exist on the left and on the right because this is a vector relation or a vector definition. Then in this case we have that OG is equal to M1 OG1 plus M2 OG2 divided by M1 plus M2. Now let's do the projection along the x-axis. In this case, we drop down the vector, and all vector quantities will carry the label x. In this case, we have OGX is equal to M1 OG1x plus M2 OG2x divided by M1 plus M2, which is equal to M1. Notice that here G1 is being measured with respect to the origin, so this is simply given by x1 plus M2 x2 divided by M1 plus M2. Now this is x1, this is y1, this is x2, and this is y2. So the value of x1 is given by 0. The value of, so let's say that this is M2, and the value of x2 is given by D divided by M1 plus M2, which is equal to M2 multiplied by D divided by M1 plus M2. So notice that the Earth represents the object 1 and the Moon represents the object 2. So now we need to determine the masses M1 and M2, or in other words, to determine the relation between them. So M2 corresponds for the mass of the Moon, which is denoted by M subscript capital M, divided by the mass M1, which is the mass of the Earth, plus the mass of the Moon. But notice that there exists a relation between ME and MM, is that ME is equal to 81 mm according to the given. So this is equal to MD divided by 81 mm plus mm. So taking a common factor mm from the numerator and mm from the denominator, we are left with D divided by 81 plus 1, which is equal to D suppressed by a factor of 82. So in this case, xg is equal to D divided by 82. And notice that here we didn't specify any unit, because usually whenever quantities are expressed in terms of another quantities, we don't express any unit. So in this case, xg, the coordinates, is given by D divided by 82. Now we need to perform the projection along the y-axis. So in this case, we drop down the vectors and each quantity will carry the label y. Not each quantity, only vector quantity. Scalars are the same for both relations. Then in this case we have OGY is equal to M1 OG1y plus M2 OG2y divided by M1 plus M2. So since we are measuring coordinates with respect to the origin, then M1 Y1 plus M2 Y2 divided by M1 plus M2. So Y1 is given by 0 as well as for Y2, so it's given by M1 multiplied by 0 plus M2 multiplied by 0 divided by M1 plus M2, which is equal to 0 divided by a number which is 0. So in this case YG is equal to 0. Now yet we didn't answer the question. We have determined the position of the center of mass. They are telling me, is this center of mass above or below the surface of the earth? So the center of mass G is somewhere here between G1 and G2 at a distance D divided by 82. But notice that we are measuring this distance with respect to the origin. In order to know whether G is located below, so this is below and this is above, in order to determine whether this point is being below or above the surface of the earth, which is this, we need to calculate the numerical value of this and compare it with respect to the radius. If it's greater than, it will be located above the surface. If it's less than, it's located below the surface. So in this case, axis G, which represents the distance OG, which is equal to D divided by 82, which is equal to 384,000 kilometers. Now because the radius is given in kilometers, let's calculate the value of axis G in kilometers divided by 82. So this is given by 4,682.93 kilometers. So in this case, the value of OG is given by 4,682.93 kilometers. So the value of OG is equal to 4,682.93 kilometers, and the value of the radius of the earth is equal to 6,400 kilometers. And whenever we say compare, we need to state whether one is greater, smaller, or equal to the other. And we need to be careful in physics. We cannot compare quantities unless they have the same unit. Both of them are expressed in meters. So in this case, it's obvious that RE or OG is less than RE. So let's say since OG is less than RE, then the center of mass of the system is located below the surface of Earth. And now let's move to exercise number 3. They are telling me the system in the adjacent figure includes a disk A, mass MA is equal to 3 kilograms and radius R is equal to 2 centimeters. So the object A, which represents a disk, have a mass MA is equal to 3 kilograms and radius R is equal to 0.02 meters. Recall that always whenever we need to convert from centimeters to meters, we divide by 100. And a rectangular plate, which is B, which is given by MB is equal to 6 kilograms of dimensions WB is equal to, so let me keep everything in centimeters. Of width B 1.6 centimeters and of length LB. Now as for the squared plate C, they are telling me mass MC is equal to 4 kilograms and of side D is equal to 6 centimeters. So it's very convenient to represent the dimensions on the figure. So let's say that this is the length LB is equal to 14 centimeters. The width WB is equal to 1.6 centimeters. This is the width. Okay, this is the length. The radius is given by R is equal to 2 centimeters. And the side of this square is given by how much? D is equal to 6 centimeters. Okay. Now they are telling me determine the position of the center of mass of the system, disk plate, and square in the given X or Y frame reference. So in this case, they gave me the frame reference, and we are done with the step number 1. So in order to determine the center of mass, usually we follow 4 steps that are given by step number 1, step number 2, step number 3, and step number 4. So in step number 1, we choose a reference, which is already done. In step number 2, we locate the coordinates of the different bodies. Step number 3 is to write the barycenter formula, and step number 4 is to project. So now we are done with the step number 1. Let's move directly to step number 2, which is writing the coordinates. So here we have 3 different bodies. Let's label these bodies to be 1, 2, and 3. So in this case, the coordinates of GA corresponding for the body 1. So these bodies are of uniform mass or uniform density. So the center of gravity of A is simply given at the center. This is also at the center, and this is also at the center here. Okay. So now as for GA, the abscissa of the point A is located here. So what is this distance? This distance corresponds to R. So this is given by R. Why R? Because this point has the following abscissa, which is located at a distance R from the origin. Okay, so this is R. Now as for the ordinate, so this is the ordinate of the center of gravity of the sphere, and it's located at a distance WB plus R. And here let me keep everything in terms of the value of the, so supposing that they are variables, then at the end we will replace some values. Okay. As for GB, so this is the center GB located at a distance LB divided by 2 as an abscissa, and then as an ordinate WB divided by 2. As for GC, so okay, now but here, okay, so now we need to specify the coordinates of this point, which is given by GC. so the center of gravity of the point C. Notice that if this is LB and this is equal also to D because this is a square, then this distance, which is from here to here, is given by what? Is given by simply this. So first of all, let's determine this distance. This distance is given by LB minus D. Okay, so we have subtracted from LB a distance D. Now we need to add the following distance. This distance corresponds to D over 2. Okay, so this will be equal to LB plus minus D over 2. Okay, as for the ordinate, it's given by WB plus D over 2. Okay, and we know the values of all of these quantities. Now we are done with the coordinates. Let's use the barycenter formula. So OG is equal to summation of MI OGI divided by summation of MI. Now I runs over the number of system that we have, the bodies in the system, so I is equal to 3, so I run from 1 to 3. Okay, so this is given by summation of, M1 OG1 plus M2 OG2 plus M3 OG3 divided by M1 plus M2. Okay, so in this case OG is equal to M1 OG1 plus M2 OG2 plus M3 OG3 divided by M1 plus M2. Now it's left to project this equation into its x and y component. Then a projection along the x-axis. So we drop down the vectors and each vector quantity will carry the label x. Now M1 represents the mass of the object A, which is MA. OG1x is simply given by x1 because we are measuring g1 with respect to the origin O, plus M2 x2, so M2 is given by MB x2 plus MC x3 divided by MA plus MB plus MC. Now the value of x1, which is corresponding for the point A, is given by R, so MA multiplied by R plus MB multiplied by LB divided by 2 plus, it will not fit here, so this is equal to MA multiplied by x1, which is R, plus MB, which is multiplied by x2, which is LB over 2, plus MC multiplied by LB minus D over 2 divided by MA plus MB plus MC. Now the value of R is equal to 2 centimeters. the value of LB is equal to 14 centimeters, and the value of D is equal to 6 centimeters, and the values of the masses respectively are given by 364. Now we need to replace these values in the following expression. Now notice that I didn't convert the distances that we have into the meters. If they are kept in the centimeter, then the unit of OGX will be in centimeters. Okay, so let's keep them in centimeters. Then MA is given by 3 multiplied by 2 plus MB, which is given by 3. Sorry, MB is 6 multiplied by 14 divided by 2 plus MC, which is 4 multiplied by LB 14 minus 6 divided by 2 divided by 3 plus 6 plus 4. Then plugging this fraction on the calculator, then it's given by 92 over 13, which is almost equal to 7.08 centimeters. Let me check again the calculation. Okay, so in this case xg is equal to 92 over 13 centimeters, which is equal to 7.08 centimeters. Okay, now we need to project along the y-axis. Then it's given by OGY. We drop down the vector and each vector quantity will carry the label y. So M1 OG1y plus M2 OG2y plus M3 OG3y divided by the factor of M1 plus M2 plus M3. Here I'm missing M3. So which is equal to M1 correspond for the mass A, OG1y, so it's given by y1 plus MBY2 plus MCY3 divided by MA plus MB plus MC. Now referring back to the coordinates, we can directly replace. So let's keep the masses the same. So y1 is given by, for the object A, which is given by WB plus R, plus MB, which is given, y2 is given by WB divided by 2, plus MC, which is given by WB plus D over 2, all of these are divided by the total mass of the system. And now let's replace the values. So MA is given by 3, WB plus R, so I didn't specify here the value of WB, I think it's given by 1.4, 1.6. so multiplied by 1.6 plus the value of r, which is given by 2, plus mb. mb is given by 6 multiplied by wb, which is given by 1.6 divided by 2, plus mc, which is given by 4 multiplied by wb, which is given by 1.6, plus d6 divided by 2. All of these are suppressed by the factor, which is given by 3 plus 6 plus 4. Plugging this complicated fraction on the calculator, so 3 multiplied by 1.6 plus 2 plus 6 and 2 so it's given by 34 divided by 13, which is equal to almost 2.62 centimeters, rounding to the second digit. Then YG is given by 34 over 13, which is almost equal to 2.62 centimeters. Now, after we have determined the coordinates of the point G, which is given by 7.08 centimeters and 2.62 centimeters, why they are expressed in centimeters? Because simply all dimensions are being expressed in centimeters. Then we can locate the center of gravity of the point G. So it must be somewhere in between these three, and this for sure depends on the densities of these objects, okay? So that's it for me in this video, guys. In the next part, we'll complete solving exercises on the barycenter formula.